From the alarm that wakes you up to the package that lands on your doorstep, our world pretty much runs on automation. But have you ever really stopped to wonder how these systems actually work? Well, let's break down the building blocks. And that's the big question for today, isn't it? We're going to pop the hood and really look at the simple, fundamental ideas that power even the most complicated automated systems you run into every single day. I mean, think about it. You've got cars that park themselves, smart lights in office buildings, and armies of robots sorting packages in huge warehouses. It all seems incredibly complex, but here's the secret. They all kind of share the same DNA. And that's exactly what we're going to do. See, if you understand the basic parts, the whole system suddenly makes a lot more sense. So first things first, how does a machine even perceive the world around it? A machine needs senses, just like you and me. And honestly, the best way to get this is with something you probably have in your pocket or on your desk right now, a modern gaming console, or even just your smartphone. To make a racing game feel real, the device can't just have a few buttons. No way. It needs to sense your every move, how you tilt it, how you turn it, how you touch it. These little sensors are its eyes and ears. Let's take a quick look at each one. First up, the accelerometer. This is the gadget that lets you steer a car in a game just by tilting your controller left or right. It's sensing that physical movement and translating it directly into the game world. Pretty cool, right? Then the gyroscope adds another layer of smarts. It detects rotation. So now it's not just about tilting, but about how you might twist or turn the device, which gives you even more precise control over that virtual car. Then, of course, you've got the simple touch sensor. You tap a spot on the screen and boom, you just changed gears. It's a direct one-to-one input, turning your touch into a command. But the pressure sensor, this takes things a step further. It's not just if you touch, but how hard you're pressing. You can press gently for a little bit of gas, or you can really push down to floor it. It gives you a much more nuanced level of control. And finally, we have the humble light sensor. This is the perfect example of automation that just works in the background. It quietly checks the light in the room and adjusts the screen so it's always perfectly readable, and you don't even have to think about it. Okay, so the machine can sense things. It has its inputs, but how does it get from just sensing to actually doing? Well, for that, it needs a brain, a microprocessor that can make a decision. Let's use a really clear example. A little robot that delivers mail in an office. Its most important job is super simple. Do not run into people. The logic behind this is the absolute foundation of all automation. So here it is, the crucial logic loop. First, it senses a person with its proximity sensor. That data is sent as a signal to its brain. The brain then compares that distance to a rule that's been pre-programmed, like a safe zone. If the person is too close, it decides to stop and sends a command to the motors. And finally, the robot acts by stopping its wheels. Sense, think, act. That is the magic formula right there. All right, now that we get the basic loop, let's zoom out. What happens when we apply this simple principle on a massive real-world scale? Well, that's when you start running into some major trade-offs. Let's take a fully automated warehouse. The advantages are huge, right? Robots can work 24/7, they process orders way faster, and they make fewer mistakes. But the disadvantages are just as big. The initial installation cost is massive. A single system failure can shut down the whole operation, and of course, there's the very real potential for job losses. And, these same kinds of trade-offs apply even to much simpler systems, like automated lights in a big building. The upside? You save a ton of electricity and money. The downside? It's expensive to install, and if one part of the system breaks, things can go wrong pretty quickly. So it's also really important to realize that not all automated systems do the same kind of job. They operate at different levels of, let's call it, intelligence or responsibility. You can basically ask this one question about any system. Is it actively doing something, like parking a car? That's control. Is it just watching something, like a weather station? That's monitoring. Or is it advising on a complex problem, like a medical diagnosis? Well, that's something else entirely. You can see this split really clearly here. A self-parking system is a control system. It's physically turning the wheel and hitting the gas. But an automatic weather station is a monitor system. It just collects and reports data. It doesn't actually change the weather. And that brings us to the most advanced category, the expert system. This is where things get really fascinating. This is more than just following a simple if-then rule. It's about applying a huge amount of knowledge to solve a problem. An expert system, like one that plays chess or helps a doctor diagnose an illness, has these 4 key ingredients. It's got a massive library of facts called a knowledge base. It has an inference engine to reason with those facts. There's a user interface, so a person can interact with it. And crucially, it has an explanation facility to actually show you how it came up with its answer. All right, let's put everything we've talked about together. We've got our sensors, we've got our processing brain, different levels of control, and safety features. Let's see them all working together in one high-stakes system that we see every day. Think about automatic train doors. It's a perfect combination of everything. You have proximity and pressure sensors to sense if a person or a bag is in the way. You have cameras for monitoring. The computer is the brain that decides if it's safe to close. The actuators are the motors that actually act, closing or reopening the doors. And, most importantly, there is always a human override, so the driver can take control. It's a complete, safe, automated system. So we've seen how these systems sense, think, and act. We get the building blocks. But as we hand over more and more responsibility to them, the final question isn't just about making them smarter or faster. It's really about how we build in the wisdom to handle the unexpected, the complex, and the things that are truly human.